Swayam Prabha. Digital India. Educated India.
In the previous lecture, we looked at reciprocity of resistive networks. It's a very important property of resistive networks, and it's also quite useful because when you interchange the stimulus and response, that is, if you have a two-port network and you apply a stimulus on the left side, measure the response on the right side, and then you apply a stimulus to the right and measure the response on the left, the ratios will be the same. That's effectively what reciprocity is. Any questions regarding what we did until the previous class? So now we'll look at a couple of more circuit theorems and then move on to two-port representations. Okay. One of the interesting things is, and practical thing that we need to calculate many times, is that we have some component, let's say a resistor. It could be a voltage source or a current source also. Okay, and let's say this is some network. Okay, which has, let's say it's a linear network with some independent sources. Okay, so many times what we need to do is to calculate the effect of component changes. Okay, so let's say this R changes to R plus delta R. Okay, so the question is, how can we calculate all the new solution to the circuit, that is new branch voltages and branch currents. Now one possibility, of course, is that we recalculate everything, that is, with the new value of the component we redo the circuit analysis. So the whole point is to try to do it in a way that is easier than that. Okay. Now again, as usual, we exploit linearity to help us calculate this without going through the whole circuit analysis again. Okay, so that's the idea. That is, with a new value of the component, it is just a new circuit and we could repeat the circuit analysis, but we would try not to do that and try to calculate the effect of changes without having to go through the circuit analysis all over again. Okay. Now instead of resistance, it could be a voltage source or a current source also. In that case, it's easier, and with resistance, it's slightly more complicated. Okay. So let's say we have a linear network with independent sources. And let me take a particular voltage source Vs. And then let's say I change only this voltage source value to Vs plus delta Vs. Okay. So in general, all the branch voltages and currents inside this will change. So Is there an easy way of computing only the changes without redoing the circuit analysis? Please try to think about this. Is there a way of calculating only the change due to the change in the voltage source? How would we go about doing this? Please try to answer this. So that's right. As Sumit answered, you use superposition, and the way to do it is, because this is a linear network, now we have already calculated the solution to this, and this Vs plus delta Vs is nothing but Vs in series with delta Vs. Okay. So now in this particular case, when we originally calculated, everything is active except this one. Okay, you can think of it as the case with delta Vs equal to 0. So what I have to do is to take the nulled circuit, this is nulled, and Vs is also nulled, and I have only delta Vs acting on the network. Okay, so now if you superpose these two, if you take the sum of these two solutions, you will end up with the solution to that one. Okay. But so now the point is that analyzing this circuit with only delta Vs is simpler than reanalyzing the whole circuit. Okay. And in fact, if you look at the branch voltages and currents in this, it will be the effect of delta Vs. That is only the changes to the branch voltages and currents due to delta Vs. Okay. Okay. Now, let's say instead of a voltage source, I have a resistor R. Okay. I have a linear network plus independent sources here, and then I change this one resistance to R plus delta R. Okay,